Section 7.8 is on using exponential and logarithmic functions. Scientific, so to speak, exponential growth and decay is modeled by the following equations. Y is equal to a times e to the kt for growth, and y equals a times e to the negative kt for decay, where a is the initial value, or the initial amount that you have, t is the time in years, k is a constant that represents the rate of growth or decay, and y is the value after the growth or decay, how much you have. So let's take a look at a couple problems here, and these are all going to be word problems. The half-life of sodium-22 is 2.6 years. Find K and the equation of decay. So we're going to start with the equation y equals a times e to the negative kt, since this is decay. So this is the half-life of sodium. So we want to have half of the original amount. So if A is the original amount, then 1/2 A is the amount after 2.6 years. So I'm going to have 1/2 A over here, because that's the amount that's going to be left after it decays. A is the original amount, times e to the negative k, which we don't know, and t is my time, my half-life, 2.6 years. So let's solve that equation. If I divide both sides by a, I get 1/2 equals e to the negative, I'm going to make that a little neater, negative 2.6k. And remember, I can take the natural log of each side. So the natural log of 1/2 is equal to, and when I take the natural log of this side, natural log of e raised to an exponent is just the exponent. So that means that k is going to be equal to the natural log of, I'll switch to decimals here for the ease on the calculator, natural log of 0.5 divided by negative 2.6, or plugging that into my calculator, k is approximately equal to 0.2666. So that means my equation of decay is going to be y equals a times e to the negative 0.2666t. That's my equation of decay. And notice originally the value here was not negative, but I have to make it negative to make it decay. So we're going to use that equation for the second part of this problem, which says that a geologist examining a meteorite estimates that it contains only about 10% as much sodium-22 as it would have contained when it hit the Earth. How long ago did it hit the Earth? So what we don't know is the time, so our variable in this case is going to be t. So using that equation, y equals a times e to the negative 0.2666t, okay? So the meteorite now has only about 10% as much as it did originally. So my y is going to be 0.1a, because that's 10% of a, equals a times e to the negative 0.2666t. Again, dividing both sides by a, I'll get 0.1 equals e to the negative kt. And solving this, I can take the natural log of each side. So the natural log of 0.1 is equal to, and remember, taking the natural log of e to a power is just that power. And recall that what I'm solving for is t, so I'll divide both sides by this decimal. So t is equal to the natural log of 0.1 over negative 0.2666, or t is approximately 8.6 years. Let's take a look at another example, and this one has actually 3 parts to it. In the year 2007, China's population was 1.32 billion. In 2000, it was 1.26 billion. So again, we have to find k and the growth equation. Because China's population increased in those 7 years, this is going to be exponential growth. So I'll use the equation y equals a times e to the kt, positive kt. So let's see. So in my original amount, let's kind of go backwards here. My original amount is going to be 1.26 billion, and then after 7 years, it was 1.32 billion. So this is the amount over here after the growth times E. I don't know what K is, but my time is going to be 7 years. Oops, 7K, because it was 7 years later. Now, taking the natural log, or let's see, actually I think what I did was I divided both sides by 1.26. I'll actually just go ahead and show this. And using my calculator, that came out to be 22 over 21. You don't always get a nice fraction like that. And if I take the natural log of both sides and taking the natural log of this side, we'll get rid of the e. That's equal to 7k. So k is going to be equal to the natural log of 22 over 21 divided by 7, or approximately 0.0066. And so my equation for the growth is going to be y equals a times e to the 0.0066 t. Next part of my problem says, when will China's population reach 1.5 billion? So in other words, in how many years? So what I don't know in this case is my t. So the amount I want after my growth is 1.5 billion. And then I'll use my, oh, you know what? I think I did that equation wrong. Hold on, let me go back here. This is wrong. Sorry about that. My original amount is 1.26 e to the 0.0066 t. Sorry about that. I did know what the original amount was in the year 2000. Okay, now that's the formula I need to use here. So my y is going to be 1.5, and then I'll use this formula here to the 0.0066 t, and now I have to solve that for t. And again, what I did in this one was I divided both sides by 1.26, and that actually gave me 25 over 21. I think it's kind of interesting that it ends up being an actual rational number here. Okay, and then I'll take the natural log of each side to solve for t. And then when I take the natural log over here, I have just the exponent. And then dividing both sides by that decimal, t is equal to the natural log of 25 over 21 divided by 0.0066, or t is approximately 26.4 years. And what they're asking is in what year will China's population reach 1.5 billion? So that would be approximately the year 2026. And the last part of this question says, India's population was 1.13 billion in 2007 and is modeled by this equation right here. When will India's population surpass China's? So in other words, when will this population be greater than that of China's? So that gives us the inequality, 1.13 times e to the 0.015 t has to be greater than the growth equation that we had for China, 1.26 times e to the 0.0066. And we're looking at 2007. Our original equation was for China's population in the year 2000, so I need to do t plus 7 because we're looking at 7 years after the year 2000. Okay, now this isn't too bad to solve, but it is going to be a little sloppy. So we're going to take the natural log of each side. I think instead of rewriting the whole thing, I'm just going to add natural log here, and I'll just add a natural log here. So natural log of this is greater than the natural log of this. So we need to go back to our properties of logarithms and break this up. So that's going to be the natural log of 1.13 plus the natural log of e to the 0.015t is greater than the natural log of 1.26 plus the natural log of e to the 0.0066 times t plus 7. I'll deal with that distribution in a little bit. We'll just leave it like that for now. Okay, so what that leaves me, so if you remember the rule I'm using is because these two things are multiplied, because this constant is multiplied by e. That's why I can break it up into addition. So the natural log of e raised to a power is just that, so I think I'll write this out. Plus 0.015t is greater than the natural log of 1.26. Okay, so this natural log of 1.13 and natural log of, sorry about that, 1.26 is just a number. So it's not a variable or anything, so it's just a number. So just go ahead and leave it there. T, and here I'm going to go ahead and distribute plus, and this ends up being 0.0462. Now, so we have a number and a term with a variable, a number, a term with a variable, and a number. So let's get all our terms with the variable on one side and all of our numbers on the other side. So that's going to give me, subtracting this right here, is going to give me 0.0084t is greater than the natural log of 1.26, subtracting the natural log of 1.13, and plus 0.0462. Looks pretty gnarly. Let's go ahead and divide both sides by this. And put that horrible looking thing into your calculator. Okay, and we will get that t, believe it or not, t is greater than about 18.5 years. So 2007 plus about 18.5 is going to be sometime during the year 2025 when India's population will surpass that of China. And our last examples here talk about the logistic growth function, which is modeled by this equation. F of t is equal to c over 1 plus a times e to the negative b times t, where a, b, and c are positive constants, and b has to be less than 1, so b is going to be a number between 0 and 1, and t is the time. Now this particular formula is used because populations cannot continue to increase to infinity. Usually they hit some sort of carrying capacity where a population kind of stalls out or the land just can't support that many people anymore. They reach a limit that's going to be represented by the horizontal asymptote y equals c. So this number on the top is going to represent what the maximum population can be. So let's take a look at an example here. A city's population in millions is represented by the function f of t is equal to 1.432 over 1 plus 1.05 e to the negative 0.32 t, where t is the number of years since the year 2000. So we need to graph the function. Now, don't pull out graph paper, we're just going to do a simple sketch of this, but I need to know a little bit of information about it. The y-intercept for this, I need to know that, is where t is equal to 0. Okay, so what I need is f of 0. F of 0. Okay, so when I put 0 into this equation for t, that's going to be e raised to the 0 power, which is just 1. So that's going to give me 1.432 over 1 plus 1.05 or 2.05, because when I put in 0 for t, makes this exponent 0 and e to the 1 is just 1. And that's approximately 0.7. My horizontal asymptote, which I'm just going to abbreviate by horizontal asymptote, is going to be the line y equals 1.432. Okay, so let's just do a little sketch of a graph. I think I can fit it down here. So there's my y-axis. There's my x-axis, and technically this is t. This axis is f of t, so let's go ahead and label that. Okay, and I'll just put a couple more. So my horizontal asymptote is going to be almost 1.5, and my y-intercept is going to be about 7/10. So I think I'll mark this as 1, and I'll mark this as 2. So my y-intercept is going to be about there, and then my horizontal asymptote is going to be right about here at about 1.4. Okay, so my line, actually I'll go ahead and do this one in pink. It's going to start right about here, and it's going to go up and look something like that, kind of level out. Okay, so don't worry too much about being super precise. I'm looking for y-intercept and what the horizontal asymptote is. Okay, so what is the maximum population here? Well, the maximum population, we can even tell that by looking at the graph. It's going to hit the line right here where y equals 1.432. So my maximum population is going to be 1.432 million people, or if you'd like to write that 1,432,000 people. And when will the population reach 1 million? Okay, so let's go back and look at the function here. So here's our function. So after how many years, so I need to find t, is this value over here going to equal 1 million? Now remember, this number is in millions, so I'm going to make f of t equal to 1. So 1 equals 1.432 over 1 plus 1.05 e to the negative 0.32t. And that's just the formula we had up above. So now let's go ahead and solve this. So I'm going to multiply both sides by the denominator. So that gives me 1 plus 1.05 e to the negative 0.32t equals 1.432. Okay. Subtract, so what did I do? Oh yeah, subtracting 1 from each side gives me this, 0.432. And I'm going to divide both sides by 1.05, so e to the negative 0.32t is equal to 0.432 over 1.05. Now, taking the natural log of each side is going to give me negative 0.32t equals the natural log of that. I'll switch to horizontal bar there. And dividing both sides then by, I'm going to move it up here, dividing both sides by negative 0.32, I'm going to get something that looks like this. So the natural log of that divided by that, the whole thing divided by that. Again, lots of parentheses in your calculator. Or t is approximately 2.8 years. And this was when the population was, t is years since the year 2000. So in approximately, so 2000 plus 2.8, so approximately the year 2003, the population of this city will reach 1 million. So in this section, we took a look at how to use exponential and logarithmic functions to solve real-life problems involving half-life, population growth, and there's actually a lot of other situations. So this is all going to be about word problems. It's not too bad. Just stick to the formulas and use the properties of logs that we've been using this whole chapter.